All right. So now we're going to talk about the little g. So we have a universal gravitational constant, which is the 6.67 times 10 to the negative 11. So we know that that one works everywhere, in the universe. Now, but how did Newton actually get the other value though? Well, other than measuring it, where does the 9.8 meter per second, the small g, the little g value come from? Okay. So now, I know that so far, we call that value acceleration due to gravity, right? The 9.8 meter per second square. But it actually has another name, gravitational field strength. So other than acceleration due to gravity, it's also called gravitational field strength. So what is a gravitational field? So what is a force field, for example? To explain how two objects can actually attract each other or repel each other without touching, scientists have used the concept called field. So they call it a force field. So a field. So what is a field? Fields are spheres of influence. They are invisible. It's technically just a math tool and intangible. So you cannot see it, you cannot even touch it. Invisible and intangible. They simply demonstrate how strong a certain force is at a certain distance. So the way we think about force field is not the same way that we think about, when you have sci-fi movies or people use a force field and then it blocks everything. Not that kind. Okay, so one analogy that we can make is by comparing a force field to the area of influence of a fire, of an open fire. So think about a fire, like a campfire, right? So we can think of it as having a heat field. Something that's invisible, you cannot see it. Intangible, you cannot touch it, but you know that it's definitely there. So for example, if you have a campfire and here's your hand, right? Here's your hand right here. Now, you know for a fact that you don't have to put your hand in the fire, which will be painful, like this. You don't have to put your hand in the fire to actually know that there is some effect on the fire. It seems like there is this like invisible thingy over here, heat, that is invisible, intangible, but you can feel it even when you just get close to it. You don't have to be exactly inside the fire. So this imaginary area of influence of heat is what we're going to use as an analogy to force field. So imagine that this is like a heat field. Okay, so the closer you get to the fire, the more you will feel the effect of the heat field. Okay, so if you get closer and closer, then the heat field will burn you more and more. But you cannot see it, you cannot touch it, yet it's there, right? So two ways we can actually make the field stronger. Number one is get closer. Okay, so as with any forces, usually that we will learn in high school at least, the closer you get, the stronger the force. So the closer you get, the stronger the gravitational field. So in this case, the closer you get, the stronger the heat field. Now, another way you can also make the field stronger is by just getting a larger base, right? A larger fire. So the larger the fire is, the further away you can get, and the further away you will notice the field of effect. Okay, so the larger the fire is, the further away we can get and still feels the field of effect. Now for gravity, okay, so for gravity, we draw it as a field that goes inward because gravity always attracts things. And we usually draw them as little arrows, as everything in physics are arrows when they are vectors. That means they have magnitude and direction. So the magnitude indicates that the field become weaker. Okay, so the field will become weaker as the distance from the Earth's center increases. So that means if you go further and further apart, the gravitational field gets weaker and weaker. So imagine that you are on the surface of the planet. Then at that point, the gravitational field is, well, 9.8 meter per second square. But allow me to not write a unit. But when you are further away, for example, what if you are over here? Then the gravitational field is going to be weaker. Maybe you're only down to 3.2. I'm making up numbers in here at this point. So the further away you are from the center of the planet is here. So the further away you are from the center of the planet, the weaker the gravitational field becomes. So if you get really, really far away, then the gravitational field will actually get really weak. Okay, so the further away you are, the weaker the gravitational field will be at the location. Okay, so technically speaking, gravitational field will drop to like 0 completely if you get really, really, really far away. That means the area of influence of gravity gets weaker as you move further and further away. So the way to actually get the equation is pretty simple. Now you think about it, we have an equation of gravity that works on Earth, mg, or on any planet's surface, if you can switch g to the other planet. And we have exactly an equation that is not exactly the same, but does exactly the same thing, but in space, right? The g, big M, small m over r squared. But technically, these two should give you the same number if you are using the little g correctly. So therefore, we can make these two equations, well, replace each other. If we put them together, you see something like this. mg is equal to big G, big M, small m over r squared. The small m cancels out. The big M, which is the mass of the planet, remains. Now, you have an equation for the little g. Now, this is the equation that you can use to find the acceleration due to gravity on other planets. So on Earth, this number will work out to be 9.8. But in other planets, you will have to substitute with the other planet's mass, and you get a number that is different. So on Mars, that number will be about 2 point something. On the Moon, 1.6. On the Sun, 200 something. So this is actually how you can you can get the acceleration on the surface of other planets, right? Other than Earth. If you put Earth information in here, you get 9.8. Okay, so remember, this used to be called acceleration due to gravity. I mean, now it's still called that, but it now has a new name too. It's now also called, so AKA, also known as gravitational field strength. Gravitational field strength. Okay, but they mean the same thing. So if a question asks you for gravitational field strength or asks you to find the acceleration due to gravity, it's asking for the same thing. Okay. Now, funny fact, when you look at the picture of the Earth, right? So let's say you go Google and you try to Google a picture of the Earth, right? Now you usually see a giant sphere, right? Something like this, a sphere, right? Looks kind of perfect, like a perfect sphere. But Earth is actually rotating, spinning. So Earth is not actually a perfect sphere. Now, because Earth spins kind of like this way, it has a little belly. Anything that spins is going to actually cause its middle part to expand a little bit. I don't know if you have made pizza or bread with your parents before. But like, you know, at the beginning, you roll your pizza dough into a ball, right? Or your, maybe sometimes it's pizza, sometimes it's bread. But if you spin that pizza dough, it's actually going to get like fatter. And then the middle is going to expand a little bit. Now, the same thing happens to Earth because Earth is actually spinning like this way. Okay, Earth is spinning this way. So it has a little fat belly, almost like this. It has a little tiny fat belly. Now, if Earth was like spinning like, for example, if Earth was spinning like this, then it will have a little fat belly over here. But hey, you know what? There is a planet that actually spin like this. Which one? One of our 8 planets actually spin like this. All the other ones spin kind of normally like we do. One of them is knocked over by something long time ago, Uranus. Uranus is actually like rolling. So instead of spinning like, you know, like any other planet that usually go like this way, Uranus is like rolling on the ground like a little ball. So most likely the reason why is because something knocked it over long time ago. So it was spinning the normal way, and then, you know, a giant asteroid or whatever locks it over, and then it go from spinning, you know, vertically into spinning horizontally. So as a result, what happens on Earth, right? So this is Earth. Let's go back to Earth right now. So as a result, Earth is actually tiny bit wider if you measure from the center to the equator compared to from the center to the North Pole. So this R2 is tiny bit bigger. Tiny bit bigger. Now you can see that in here. R2 is to the equator. R1 is the one that we have to the North Pole, from the center to the North Pole. How much is it off by? Not too much. It's off by, what was that value? 16 kilometers? Not that much. It's not off by like an insane amount. So if you measure Earth's radius this way, it's shorter than the Earth's radius this way by about 16 kilometers. 16 kilometers from here to Surrey. But it's still not like, it's not zero. Earth is not a perfect sphere. Okay, so that means our little g value at these two locations are actually going to be slightly different. And that's what we're going to do right now. Find out the acceleration due to gravity if you live in a country near the equator or if you live in North Pole. Now, we are in Vancouver. Where are we? We are kind of somewhat like, you know, Vancouver is around here, right? We are not at the equator. We are not on the North Pole, but we are a bit closer, I think, to the North Pole than the equator. So we are not, so we are somewhere in between, like in terms of the radius to the center of the Earth, somewhere in between. Okay, so let's do that. So we're going to get G1 and G2 using the gravitational field equation, Gm over R square, except one of them you will use R1 and the other one you use R2. Okay, so the first one, 6.67 times 10 to the negative 11, mass of the Earth, 5.98, 10 to the 24. And distance. You know what? I'm not going to write down G anymore. So from this point on, you should know G is that. I'm not writing it down. Save me a lot of space. Again, this G is on your formula sheet on the back. So radius, 6.37 times 10 to the 6. And that's measured in meter. You have to square it. So this will give us one number. So you can try on your calculator. And then B, which is G2, will be another number. 5.98 times 10 to the 24 is the same. Distance is different. 6.386 times 10 to the 6, and then squared. Okay. So the closer you get, the stronger the gravity is. So that means at the equator, the answer should be stronger. Now, and it turns out, yeah, it's approximately 9.83 at the equator, but only 9.78 on the pole. So there is a small but actually noticeable difference. Now, in class, what we have been doing since unit 1, right, is assuming that the value is 9.8. Well, the reason why is we are somewhere in between. So we are not at the equator. We are not at the pole. We will use 9.83 if we're at the pole. We are not at the equator. We will use 9.78 if we are at the equator. We are somewhere in between those two locations, right? The location of Vancouver is somewhere in between those two. So we are using approximately 9.8. So in this last question, we want to calculate the gravitational field strength at the moon's location. So at the moon's location. So Earth is here. The moon's location is somewhere here. Okay. So what is the gravitational field strength at that point? Now, so the moon is like, somewhere over here. Okay. Now, but be careful though. We actually don't care about the moon. We are just using the moon for its location. And also, the location that they gave us is sadly not the correct one. It's measured from the surface of Earth. And if you have been paying attention, you know what the problem is. This 385,000 kilometer, which is not even useful because we have to change it to meters, so add like 3 more zero to it, is not even a useful number because it's measured from the surface of the Earth. And we need the distance from the middle of the Earth. Well, luckily, that means we're only missing this part, which is the radius of the Earth. So if you add radius of the Earth to this, well, at least we can get the total distance. The radius of the Earth is 6.37 times 10 to the 6 meter, and you add it to that 385 million meter. So the two things together. So we're going to get our actual radius, add them together, which is going to be 3.914 times 10 to the 8 meter. Okay, so we're going to have a pretty big number. But this is a number that we can actually use, not the one that he gave us, not Earth's radius. We have to add them together. So don't you just, hate it a little bit when they don't give you the center distance? Then you have to worry about, okay, what planet am I from? Do I have to add the radius? Now, but other than that, the mass of the Earth is the only thing that matters, not the mass of the moon. If you look at the little g equation, it's g big M over r squared, not small m. Okay, so big M in this case is the planet that you're orbiting, which is the Earth. So don't just put in whatever mass value that they give you. It's the mass of the center object, the object that's actually from the gravity that you actually measured. Okay, see. So G, mass of the Earth, and distance. And square. Okay. Again, I'm not writing out G because you should know G is on the back of the formula sheet from now on. This is going to be a very tiny number, though. It's going to be a very tiny number. Well, I mean, not insane, but 0.0026 meter per second square. So, like, compared to what it would be if we are on the surface of the Earth, 9.8, this is thousands and thousands of times smaller. But even though the acceleration is so small, the moon is still attracted to us by that. Like, think about it. So even though the acceleration is small, but the moon is not going away. Because of that tiny acceleration, the moon is still orbiting us every day. Thanks for that, right? Otherwise, we won't have a moon. We won't have a satellite. Okay,